So we have been doing a lot. Let me just summarize what we've been doing so far. So basically, what we've been looking at for the past few weeks has been to be looking at how to design beams. All right, and normally for beam design, we are looking at so we are looking at designs. So we are looking at designs which so we're looking at designs for bending, sorry, and then designs for shear. Okay. So that's okay, so design for bending, design for shear. And for design for bending, we are looking at longitudinal. So if you have a beam, right, the rebars in there, okay, along the length of the beam are the longitudinal rebars. Okay, so we design, and those are what prevent bending failure. Okay. Then for the design for shear, we put in stirrups or links, vertical stirrups, okay? And also design them to prevent shear failure or diagonal tensile failure. All right, so that's what we've been looking at for the past few weeks. And largely, we've been focusing on simply supported beams. All right, so straightforward beams and all of that, okay? So I think generally we looked at, and anytime you are designing a beam, you also focus largely on the cross section. All right. So the cross section in most cases can be rectangular, or you can have a T section or an L-shaped section. So these can be the different sections that your beam can be in, depending on what we are looking at. And bending usually occurs, or bending failure. So in terms of bending, so bending failure occurs in a tension zone. Okay. So the tension zone depends largely at, or depends largely on which parts of the structure we are looking at. All right. So for a simply supported beam, right? So for a simply supported beam, where you have load acting downwards, our tension zone will be in the bottom section. Okay, so the tension zone will be in the bottom section, and the compression zone will be at the top section. All right. The tension zone can vary, depends on the position of the load and also which part of the beam we are looking at. Okay. So basically, the lecture 5 and 6 largely talks about how to design simply supported beams for both bending and shear. All right. And this is how, when you go on site, this is how we see all these rebars, or as a layman will see, the iron rods being placed with the cage, which is the shear links all around it. Okay. So let's move to something slightly different. What if instead of this way. So what if instead of simply supported beam, we look at continuous beams? Okay. Because anytime you go to a site, you hardly come across simply supported beam. All right. When you go to an engineering site, you realize that the beams, columns, and slabs, they are, what's the name? We usually cast them together, right? Or they are cast in situ on site. Hardly do we see them being prefab and then assembled on site. They're mostly cast in situ. And because of that, you'd realize that the entire structure behaves as one, or they act together. Okay. So if they act together, it means that they pretty much will begin to form what you call they form what you call a continuous load bearing structure. Okay. So because of that, we can take advantage of the fact that we usually cast our concrete in situ, and then by casting them in situ, we end up with a one big system. All right. So because of that, we can also have the case whereby the reinforcement should also be continuous. Okay, so the reinforcement must be designed and detailed as continuous. Okay, to take advantage of the fact that the structure is acting together. All right. To maintain such continuity. Okay. All right, so let's look at a typical continuous beam. Let me see if I can maybe draw something nicer. Okay. I think this looks good. Okay. Let's say we have columns going along the span. My drawing might not look too accurate, so don't hold me for it. Okay. Just to explain an idea. Okay, so this is like a typical beam column arrangement that you find on site. Okay. Now you would realize that if you are to draw the bending moment diagram, all right, this is how the bending moment diagram usually would look like. So pretty much what this means that the bending moment, let me just put that over here. Bending moment is generally generally a series of sagging and hugging moments. Okay. So we can see that when you are in the spans, you are looking at sagging moments. Okay. So in the spans, the moment is sagging. Then when you are in the support, the moment is hugging. Let me finish my drawing. And then at the support, the moment is sagging. Okay. So we have these types of moments, sagging and hugging moments. So this is a different color. Here you are sagging. And then this, you are hugging. Okay. What this means is that, so we call this the spans. Okay. And then this is the supports or over the supports. Okay. So where the columns are located are the supports. All right. So largely, when you look at a system like this, which you guys have come across some examples of these using the three-moment equation method in second year, or the moment distribution method, or the slope deflection equation method. All of these are different ways by which we can analyze a series of statically indeterminate, or what you call continuous beams. Now, you would realize that if you're looking at the spans, so for spans, typically the tension zone is at the base. Okay. And then for supports or over supports, typically, again, because sometimes it's not always the case, but then normally this is what you have. The tension zone. The tension zone is, no, not saying B, let me say bottom. Okay. At the bottom for the first one, then at the top for the second one. Okay. I may not see your text if you send me a message, I might not see. But I've joined with another name, same as my name, but that one is not the host. So you can send the text to that one. I'll be able to see when you send the text to that. In case you want to ask a question, or maybe you can unmute or whatever. All right. So this is what happens. Okay. So again, if I let me just redraw this or copy it rather. All right. So this is what we have. Okay. So let's so green. Let's say green is tension. Let me just use green for tension. Then let me use the red for compression. Okay. So what happens is that in the in the span area, this zone, the zone here is in tension. Okay. So just that as you go towards the support, your tension zone reduces, right? So it reduces, then it comes up again, then it goes down, then it comes, it reduces before, then, oops, let me draw this thing well. Okay. Comes down, then it goes up, then it comes down, it goes up, and it comes down. Okay, so this is a tension zone. This is a tension zone. All right, so that's how we're able to identify the tension zone. And then with, let me see if I can get this one right. Um, then over the supports, your tension zone will be here. Right, so over the supports, your tension zone is somewhere here. So this is a tension zone for the supports. All right. So the supports do have a tension zone. Okay. All right. So that's one thing to take note of. So for the spans, the tension zone is in the base, and then for the supports, the tension zone is up. Okay. Because of the fact that hugging moments occur at the supports. All right. So basically your moment diagram or the moments at supports is bending upwards. So because it's bending upwards, the tension area will be the upper portion. Okay. Then the compression. So this will be the compression zone. This will be the compression zone. Okay. So this is typically what happens in a beam or a continuous beam. So there's certain portions which are in tension, certain portions which are in compression. All right. And normally, if you take, so this is just on the side. Normally, because we have slabs and beams being cast together, how do I draw this? Okay, so let me put this here. So where stagging moments occur, we can take this option that the beam and slab act together. Okay, so that's like mid-span or somewhere in the span of the beam where sagging moments act together. And as such, the beam can be designed as a T-beam. Okay. So again, if you have, let's say that you have, let me just draw it a different color. So let's look at the, so we have this as a, so this here is the slab. It is a slab. And then we can have the beams. Okay. So these are the beams. All right. But because we cast them together and then let's say if we take this beam for, it's difficult to draw like that, but if we take this beam, for example, all right, this beam would be pretty much what we have here. So if you take the beam and you have to draw the longitudinal direction, so let me just show you how this will look like if I'm, okay, I don't have what I'm looking for. I'll make a copy of this. So that just show you how this will look like. Okay, so this is fine. So for that particular beam, this will be the way the beam looks like. Okay. So maybe this is a beam, and then we have the columns running through like that. So we have columns running through. I have columns running through. Let me just exaggerate the column positions a little bit. Okay. So that it doesn't look like I'm copying that of there. Maybe we have one at the end. Okay. That should be enough. Okay, great. So if we are designing this beam, okay, let's say pretty much this beam, that's what I've drawn over here. There's that beam. When we get to the midspan of the beam, so let's say maybe a midspan can be anywhere. Let's say maybe 1, 2, 3, 4. So this is at the grid lines passing through this point. All right, so this is like what usually happens. Now we draw. All right. Okay. So if I'm looking at span 1, 2, maybe I'm designing the beam somewhere in this zone. Somewhere in this zone. All right. Because the bottom part is in tension and then the top section is in compression, we want to take advantage of the compressive strength of concrete in compression. All right. So we would design this section here as a T-beam. So that's like the basic way to explain. So we'll design this section here as a T-beam. And that's or in effect, it's easier to see it in the cross section. I'm just trying to figure out how to draw, but like that's the idea. That's not the right representation, but the idea is that where you have slab and beams working together, so there's a beam working together, you can design the cross section of that beam. So if let's say we are looking at somewhere around midspan, then this is what we do. Okay. So that's how we normally design beams and slabs together when that portion, when the base or the bottom is in tension. Okay. So that's something to take a note of. The next point would be is that but at support, where hugging moments okay. The support beams or the beams at support are designed and detailed as rectangular members or as rectangular sections. Okay. So it means that if you are designing the beam around grid line 2, then the beam will be designed as rectangular. So it's still the same spot, all right, but now we are closer to the support, or we are where the support is. So it wouldn't be T-beam anymore, but it would be a rectangular beam. So take note of the differences, the hugging and the sagging. Okay. Again, as I said, so this, let me put this into brackets. So the hugging moment will cause tension in the slabs. All right, so let's see. The third point will be that usually, if you're looking at the cross sections, because a typical T flange will have a larger size and also a larger compression area than the a rectangular beam, it means that the moment resistance of concrete for a T beam will be higher than that of a rectangular beam. So what this also means is that when it comes to moment redistribution, which I think it's in one of your videos, when we are trying to redistribute moment to ensure that your structure can still be able to accept higher moments, we want to redistribute the moment in such a way that for moment redistribution, we can reduce the support moment, cause reduce support moment, oh, and then possibly increase the design span moments. Right. So I try to take advantage of moment redistribution. Okay. So with that, because our goal is to ensure that there's continuity of reinforcements, so continuity of the reinforcement, it is important to understand how the envelope of moments behaves. So this diagram here is very, very important to us, okay, which I have been able to, which I've shown over here, that the difference in shear and in the tension, all right. Normally, if you have, when it comes to reinforcement for bending, we have two types. Either we have the singly reinforced, where you are only required to reinforce the tension zone where tension failure is likely to occur, or you look at the case whereby you need double reinforcement or doubly reinforcement because concrete is likely to fail in compression and you want to, or the concrete compression is not enough to resist the loads coming onto the structure. All right. So we have these two loading arrangements. So let's see a typical, I'm going to copy that information from somewhere. So let's say a typical rebar arrangement, just to explain the concept to us. So here we have the hopefully this thing comes okay. So this is a typical rebar arrangement for um a continuous beam. All right. So again, red means compression, green means tension. So oops, so here in the spans we can see the tension for the spans or the tension rebar for the spans. And this is what T220. All right. Then if you look at the support, which I think is the one that is critical, because tension over support is at the top. So this zone is tension, this zone is tension, 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 and tension. So over support, we have tension, and then at the spans, the tension is at the bottom. Okay. So you realize that with the tension zone over the support, we have two rebar arrangements. So we have the T1 and then we have the T2. So maybe the top one could be the T1 and the top down value can be the T2. Okay, so these are your what's the name? Your tension rebar for the different sections. So you can also see something very similar over here. Okay. And again at the base. Okay. Somewhere in here you have oops, different color. Somewhere in here you have compression. So it's possible that this particular structure does not need compression reinforcement. Okay. Then here at the base also, you also have compression reinforcement. So these are the zones that need compression reinforcement. The same applies to here and then here. Okay, so ideally, compression reinforcement are smaller compared to tensile reinforcement, or sometimes we don't even need compression reinforcement. Okay. The reason why sometimes we have to put rebars at the top of the beam, which we call them hanger rebars, is so that we can have something to hold our shear links. Okay, and that's about it. Okay. Now let's look at the design of continuous beams. All right. Design of continuous beams. Whatever we learn right now ties in with slabs in a way, but I would discuss with you maybe what goes into it a bit more. Okay. So let's look at the much simple process, okay, because design in itself is repeating or repetitive. Okay. Normally, you find yourself with so let's look at these options. Normally, when you're doing design, you usually have the loads are usually uniformly distributed. Okay, so an example would be you have maybe you have this beam, these are your supports. All right, then you realize that your loads on them is pretty much the same UDL all the way to the end, and that is very very common. All right, if I put up a house, you'll realize that your live loads, which are maybe could be, let's say, the occupants in the house or whatever, are pretty much the same, right, across the entire length of the building or the entire area of the building. Yeah, sorry, I seem a bit tired. I've been teaching since 10 a.m. All right. Okay. So if the loads are usually uniformly distributed, and then the next bit will be that the spans are equal or large spans are equal. Okay, so it means that this oops. So this L, that L, and this L are the same. Okay. And that's also quite common in structures where you find out that the spans are quite uh, equal. And also, normally, your live load is always less than normally than the dead load. So where imposed loads or live loads is not greater than the dead loads. So if you have a structure that's able to satisfy all three conditions, then your analysis. So all of this is just to help us to do simplified analysis. Okay. Assuming that your loads are not uniformly distributed, assuming that the spans are not equal, or maybe imposed load is more than dead loads, then you have to do proper analysis of the beam. So you have to choose either the three-moment equation method, or choose the moment distribution method, or choose the slope deflection equation method, or the matrix method, or whatever method they are there, or the force method like the influence lines. We did our force method earlier, was the exact name. So there are different options available, and you do a proper analysis of the structure, find your shear force and bending moment values, and then draw respective diagrams. Okay, that's what we would normally do. But if all three conditions are satisfied, then we have a much more simple process in the analysis, okay, which is also quite common. Okay. But usually for large buildings and for more complex buildings, you might want to do the analysis do a thorough analysis process. All right. So let's say I have this beam. So let me just exaggerate it. Okay. So these are my supports. Now let's see. Let's give them nice names, and then so the support at the ends, these supports at the ends, they are called exterior supports. Okay. Then these supports are what you call the first interior support. So they're the supports you would meet when you are right after the exterior support. The first interior support is the one right after. So there are two of them. Then we also have the interior supports. First interior supports are also interior supports, but just that because of where they are located, we just show or we differentiate it from the rest. Okay. All right. So why is this important? This is important because we can take this information and then write simple equations for moment and then for shear for a beam of this nature. So let me just take you off, and off. Great. Maybe I might have to push it down a little bit. So let's look at moments, for example. Okay. So here we have a beam simply supported on all ends. All right. So if you're looking at moments, so for moments, okay. So let's do with at supports. Okay. So let me look at supports. Okay. So I still need to move it around a little bit. For supports, over the exterior support, your moment is 0. All right. At the first interior support is minus 0.11 FL. I'll explain that shortly. Then, so it's 0 over here again, so it's minus 0.11 FL. And then, so over the interior support is minus 0.88 F, minus 0.08, no, sorry, FL. This is minus 0.08 FL. Okay. Then at spans or at mid span, let me change the color of that one. So at mid spans, here it would be so 0. What do I have? 0.09 FL, sorry. And then so we call this one let me label it over here. What color should I go for? Okay, so this side is called the near so this is near middle of end span. Okay, my pen is messing up. Okay. So this is near middle of end span. So that's what will give us a 0.09 FL. And then this is what near middle of you can say first interior span. Okay. And then this one will be near middle of interior span. Okay. So these are how we name them. So here, this will be 0.07 FL. Then this would be again 0.07 FL, 0.07 FL, and then 0.09 FL. Okay, let me just cross check this information quickly to make sure that I have the right set of data. So the moments at the outer support is 0. Moments first interior support is hopefully I didn't get it wrong. Okay, so 0.09 is correct. Minus 0.11 is correct. Okay. I think largely minus 0.08. Okay, so I think I'm okay. Hopefully I haven't made the mistake somewhere. And then our mid spans is 0.9, 0.09, okay. And then 0.07. Okay, I think I should be correct. I should be correct. If for some reason I'm not, I'll let you guys know. But I think generally I should be correct. Okay. Hmm. Okay, all right. So let's understand what the F and L. Okay, before that, so this is for moment. My moment. So this is for moment. Now let me do the one for shear. Then I'll explain what the F and L stands for. Okay. So this is for moment. Now let's look for shear. Okay. So let me just let me paste whatever I had earlier. Okay, great. It's doing the same thing. So for shear, what we are concerned with, usually shear will be maximum at supports. All right. So the shear, um, so the shear on at the outer support will be 0.45 FL. Then the shear um, just on the left will be 0.6 F. No, no L, sorry. Was it shear 0. So the one 0.6 F, and then just on the right, the shear will be 0.55 F. So you go through some books and they just assume that both left and right of any joint it's the same. All right. So just take notice of that. Okay. Um, so here, this one's is going to be 0.55. Hopefully I don't run out. Okay, let me do this way. One should be top, one should be up. 0.55 F. Then here's 0.55 F. 0.55 F. So the same thing here is 0.45. Then on the right is 0.6 F. On the left is 0.55 F. 0.55 F and then 0.55 F. So these are the shear force values, all right? And since it's a UDL, we do know that our shear force diagram will look like this. Okay. This is how our shear force diagram will look like. All right. And in the case of the moment, typically this is how our moment will look like. All right. So at least we have an idea of why, so that we don't go through the normal, what's the name? The normal analysis that we do. Okay. So this is more like a simplified version of what we've been looking at. So we saw one example just to explain what the concept is, and then I think we can see what we do afterwards. Yeah, I don't want to promise something. All right. So let's look at an example. So let's say, let me just see if I can type this. Times in which there was a text to a speech to text component of this particular app. So a beam is 300 millimeters wide by 660 millimeters deep. Okay. So with three equal spans. So okay, this is going to help us to explicit the concept in the transverse direction. Let me just put that to writing. The transverse direction, the beams are at 4 meters centers. Okay. With an 180 millimeter thick slab. Okay. As shown, I'll try and draw it. So our QK, which is a live load, is giving us 50 kilonewtons per meter, and the GK is given to us as 85 kilonewtons per meter. So this also includes the self weight, right? We'll look at some of these things. Include self weight once we start with the design. I mean the take home design. All right. Okay, great. So our FCU is 30 newtons per millimeter squared, and then Fy is 460 newtons per millimeter squared. Let's our FYV. Since we've not watched the video, some of these terms will look a bit strange to us, but that is fine. After you watch, everything will come full circle to you, right? This is 250 newtons per millimeter squared. And this for the links. So we are being told that the minimum cover to reinforcement is 20 millimeters. Okay. So let's look at how to solve this problem. Okay. So we have the QK, we have the GK, but so this is our beam right here. So these are the supports. Crossband. So let's see. Oops, I didn't do something I was supposed to do earlier. Okay, that's fine. I'll just move things down a little. Okay. Okay, so I had to explain what the F was. Sorry, okay. Usually we find W, right, which is the ultimate load. All right, W is the ultimate load or the design load. The design load, which is equal to 1.4 GK plus 1.6 QK. All right, so that's the W. Now, typically your W will be in kilonewtons per meter. Okay. But to find sorry, what we call the total ultimate load on a span, so that will be our F. Okay, the F that's in the table, where F is simply W times L. All right, so after you find your W, you can multiply that by L. Or another way that you can do is that you can find QK, where QK is simply GK times L. Sorry, big QK is equal to small QK times L. And then big GK is equal to small GK times L. All right. So what this means is that then your F will be equal to 1.4 big GK plus 1.6 big QK. All right. So either you go with this option here or you go with this option over here. It is the same thing. All right. And then the L will be the length of the spans. All right. So here each span is the same as the previous spans. So this is your L, and your L, and your L. Okay. All right. So going back to my example, I can then, so I have an L here. Where L is 5 meters over here, 5 meters over here, and 5 meters here. All right. So we have this system in place. So let's find our F. Okay. So solution. Okay. So there are UDLs on this system. So two types or two main UDLs. Let me just show that with a different color. So the first one, so your QK is 50 kilonewtons per meter, and your GK is 85 kilonewtons per meter. Okay. So our W will be 1.4 times 85 plus 1.6 times 50. All right. And if we do the math, that will give us 199 kilonewtons per meter. Okay. Now let's find F. F is equal to W times L. It becomes 199 times 5. And that will give us 995 kilonewtons. Great. Let's do something interesting. So here we want to design the beams, the beam, but we can design it span by span. All right. So we know, so in terms of the moment, M, this will be 0, this will be 0. Okay, at least from our previous computations. At mid-span, we get 0.09 FL. This is minus 0.11. FL, this is also minus 0.11 FL. Then here is 0.09 FL. And then this will be, what's that, right? 0.07, right? Yeah. So this is 0.07 FL. Okay. So it means that you have to design the beam for, so let me call this one span 1, span 2, span 3. So you have to design the beam for bending in span 1, bending in span 2, bending in span 3. They're also designed for moment over the support. So 5 calculations we should be repeating will be done. Okay, but because some of them are similar, you can group them together and then you end up with 3 different calculations. Okay. So we are going with this approach, this simplified approach, because all 3 conditions have been satisfied. We are using a UDL. The spans are the same, and also you'll see that your life load is not more than the dead load, or the dead load is more than the life load. So all 3 conditions have been satisfied. Good. Okay. So let's look at design for bending or for bending moments. So one, we can see that the mid span of the first and third spans are the same, right? Okay. So it means that our moment M will be equal to 0.09 FL. So this will give us 0.09 times an F of 995 times an L of 5 meters. And this will give us a moment of 448 kilonewton meter. Okay. Here, because there's a slab, all right, from the question, there's a slab on top of the beam, all right? And because we are looking at sorry, because we are looking at what's the name? Where would this equation be? Okay. So so notes. Let me put in the notes in green or the notes in red rather. Okay. So notes. Slab is placed over the beam. So at mid-span, beam is designed as a T-beam. Okay. So here, because there's a slab on top, we are to design the mid-span as a T-beam. All right. So let's look at, so this is the cross-section. Now, I think for I think it's lecture 4, lecture 5, one of them, we need to find the effective width, BW. Sorry, the effective width of the flange. So let's say just a B. Okay. And B is either the minimum of one of these, either the actual flange width, which we were given in the question, or the width of the bottom part of the web plus L over L over 5, sorry. Okay. Okay, or should I say LE rather over 5? Okay. So now let's look at what L is. LE from previous notes was given as 0.7, or generally LE is equal to 0.7 L. Let me see if I can find that lecture. Take you guys back to it and see if it's there somewhere. No, it's not here. I think it should be somewhere here. Hopefully, you can see where my information is coming from. It takes a bit for these things to load sometimes. Show yourself. Oops. Okay, so I think it's somewhere here. Okay, so I'm basing whatever I'm looking at on this equation, right? So here I said LX. So I have this equation right here, right? So this is what I'm using since I'm looking at a TB. So I choose the minimum of the actual flange width, or the width of the web, plus LX over 5, or LE, effective length, okay? And then we say that the effective length LX is usually taken as 0.7 L. So that's in your notes already. So I'm just taking the information from that side. All right. Okay. So let's see. So this here will be equal to 0.7 times 5. All right. So 70% of 5 is what? Do you have a calculator somewhere? I think I do. So that would be 0.7 times 5. That'll give me 3. Oh, 3.5. Interesting. Meters. Okay. All right. Oh, all right. Okay. So let's look at the actual flange width from the question. Okay. So the um, so it says that in the transverse direction, um, the beams are placed. How do I draw this for you to appreciate what is happening? Okay. So let me see. I want us to picture what is happening. So let me come up with some idea of what it looks like. Okay. So this is a slab, and then there are beams beneath the slab. Okay. So something like this. And then the beams are placed at centers like this. Okay. So the distances from each beam is 4 meters. But for each beam, there's a column like this. How many do I need? Okay. So for each beam, these are the columns on the beams. Okay. So maybe this makes sense a little bit. Okay. So we have these sets of columns. Okay. And the columns are spaced this way. Okay. So each one is 5 meters. Okay. So what we are looking at this beam right here. Let's say we are looking at this beam. So the actual flange width will be half of this and then half of that. So the flange width here is 4 meters. So 2 from each side will give us 4 meters. Okay. So the actual flange width is 4 meters, all right, which is pretty much the same as the centers of how the beams have been arranged. Okay. Now, so now let's look at BW. BW was given to us as the width of the beam is 300 millimeters. So BW is 300 millimeters. So our B here, this will be equal to 3. So let me change everything into meters, sorry, millimeters. So this is 4,000 millimeters. It becomes 300 plus 3,500 over 5. And this will give us 1,000, I think, millimeters. You can always cross check and see 300 plus 350 divided by 5. Great. So the lesser of these will be this. So our effective width is 1,000 millimeters. Okay. So why do we need this? Let's go ahead and look at it. All right. So we need to first find K. All right. K will define whether we need compression reinforcement or not. Hopefully not. So K is equal to M over BD squared FC. Okay. The moment, we got the moment to be what? 448 kilonewton meter. So 448. Let's convert everything to newtons and millimeters. Our B will be the 1,000. Okay. Times a D. We're given a D of 6. We're not given D. So let's assume D for now. So coming here, this is our beam. Here is 300. This whole thing is 660. All right. So let's assume that we are using tension reinforcement. So here becomes our D. All right. So let's create a scenario for D. Let's create a scenario for D and C. Let's assume that we might end up using a bar diameter of 32. We are assuming, right? I mean, everybody can have something different. And it's the reason why I'm saying that 2 persons cannot have the same design. Okay. So D is going to be our clear, the clear cover is given to us as what? 20 millimeters. So the cover here is 20 millimeters. So D will be 660 minus half of the 32, then minus 20. Okay. So let's see if I'm correct. So 660 minus 16 minus 20, that'll give me what? 624. I don't want that. I want to use an easier. Let me see. Come up with something. I want to take this 60 away. All right. I'll take the 60 away. Okay. So for now, but usually this is how we calculate for D. All right. You assume a certain diameter for your bar, and then you use that information to calculate for D. Okay. So let's assume, let me just put that over here. Let's assume the effective depth D is 600 millimeters. Okay. But the way I did it earlier is actually how to find D. Okay. So in a proper design process, that's how we find D. So let's say D is 600 times an FC of 30, and then K will be equal to 0.041. All right. And since this one is less than 0. Oh, this is not more than 0.156. It means that no or only tensile steel or reinforcement is needed or is required. Okay. So once we find K, we need to find AS. All right. So AS, which is the area of steel required, is equal to the moment divided by 0.87 Fy times Z. But what is Z? Z is equal to D into bracket 0.5 plus square root of 0.25 minus K over 0.9. Okay. And I think Z, I mentioned that Z has limits, all right? Z cannot go beyond certain ranges, 0.775D and then 0.95D. All right. Yeah. So Z, I don't think I mentioned that earlier, but Z ranges between these limits, 0.95D, no, 0.775D, and then 0.95D. So this is the highest we can have Z to be in, all right, or the lowest, all right. So if your Z falls below 0.77D, then you need to find or use that value, all right? And if Z goes above 0.95D, you use that value, all right? So 0.95 times 600 in this case will give us 570. Okay, let's put that over here. Since our D is 600 and 0.775D, which is 600, will give us 465 millimeters. Okay, so this is a range in which Z can be in. So now let's find Z and see range for Z. So Z is going to be 600, 0.5 plus 0.25 minus K, which is 0.041. So let's see what we'll get from here. Square root of 0.25 minus 0.041 over 0.9. Okay, and then plus 0.5. All right. So it becomes 600 times 0.226. And you see that this value is way is lower than what we need. So what will we get? So times 600. So this will give us what? 135. Hopefully I'm not getting any wrong answer. I'm just check what I calculated earlier to make sure that I have the right information. Okay. have I done something wrong? Okay, I have to check my calculations again to see if what I did is right or it's wrong. 0.25 minus k, what is 0.041 over 9? 0.9, square root of that. And then plus 0.5. Okay, so I think I made a mistake, and that makes sense because I can't get the answer I was trying to get. So let me just do the calculations again. 0.25. Or is someone doing the math on the side for me? No, no one yet. Okay, so 0.25 minus 0.041 over 0.9. Okay, plus 0.5. So this will give me times 0.952. Okay, this makes sense. So this will give me 571 millimeters. Okay, so since Z is more than 0.95D, use 0.95D. Take a note of that. So my AS here will be equal to the M, which is 448 times 10 exponent 6 divided by 0.87 times an FY of 460 times a Z value of 570. Okay. So once we have that, that will give us AS of 1964 millimeter squared, right? From these calculations. So let's assume that we are looking at 25. Let's say using 25 millimeter bar. The area for one of them will be I think 500 millimeters. All right. So the number of bars needed becomes this 1964 divided by 500. I think there's a table for this. I'll try and look for the table for us. So this becomes 1964. So that you don't have to be doing these calculations all the time. This is equal to 3.93, and that's approximately 4 number. So in effect, provide 4T25. Okay, 4T25. Someone can also decide to use 20 bars or even the 32 bars, and it still works. All right. So if you provide 4T25, then your area provided, ASP, will be 2000 millimeter squared. All right. So that's for the span, the first and third span. All right. So all that we've done so far is for the first and third span. They also do a similar calculation for what's her name? The interior span. All right. But let's not jump. So let's do the over the support since they're the same. So right. So the first and then the first interior support, right? So or over the supports. So let's say II. interior supports. Okay, but because that one, the tension zone is in the slab, we design as a rectangular section. I mentioned that at the beginning of the class. All right. So let's find the M. M is 0.11 FL. All right. The negative here just indicates that it is a hugging moment. But usually when you're finding the moment to find your K, you don't indicate the negative, right? So this is going to be equal to 0.11 times an F of 995 and L of 5 meters. We get 547 kilonewton meter. Okay, so please, this is a hugging moment, just in case we're looking for that information. So let's find K. K is M over BD squared FCU. So it's the same steps that we go through. All right. So it's 547 times 10 exponent 6 over the B. So here, use B of B. Okay, so our B here would be 300 millimeters. Okay, it becomes 300 times 600 for let me make sure that I have everything right. So, okay, let me draw this on the side. So with that one, your tension reinforcement will be up here. Okay, so just take notes. And then your so this will be your D. Okay. So it's like it's an upside down version of what we've been looking at. All right. So it is critical to ensure that you know where your tension zone is and also where your compression zone is also. All right. Very important to us. And again, the D can vary. So let me put this into a bracket. D can vary for sagging and hugging. All right. So these are allowed to vary. Okay. Depending on what what's the name, what rebars you are using, and then all of that. Okay. And how you are arranging your rebars. Okay. So let me use that as an example. So in this case, our D is 580. We'll see why I use 580 shortly. And then squared times an FCU of 30. So this will give us 0.18. Okay. So once we use 0.18, we'll compare with 0.156. Okay. And we can see that 0.18 is more than 0.156. And what this means is that compression reinforcement is needed. Okay, so compression reinforcement is required, and once compression reinforcement is required, it means that we need to find AS prime. Okay, So AS prime is for compression reinforcement. So over the support, your compression zone is here. So this is your compression zone. This is the compression zone. Okay. So AS prime is going to be M minus 0.156 FCU BD squared. Okay. Over 0.87 FYD minus D prime. Okay, so we have this equation right here. Now let's find D prime. So we'll need compression reinforcement. So this is compression reinforcement. So our D prime will be the distance from the compression reinforcement to the compression section of flange. So this becomes our D prime. Okay. So in design, you have to as an engineer in design, you have to come up with all of these values. Okay. So this is what our M is. We got M of 547. So 547 times 10 exponent 6 minus 0.156 times an FCU of 30, a B of 300, a D of 580, all over 0.87 times an Fy of 460. Our D is 580. Let's say that let D prime be equal to 50 millimeters. So 50. Now, if you do all of this, it means that your AS prime will be equal to 352 millimeter squared. Okay. Usually, you also have to compare with a minimum. Okay, I'll look for that value and then I'll add it to the notes. So a minimum area, A min. Okay. So that if your AS prime is more than the minimum area required, then great. If it's less than the minimum area required, then you go for the area minimum. Right. So let me just put that into this table. Okay. So A minimum is equal to 0.0013 BH. So A minimum for Fy equals 460. Okay, then A minimum is equal to 0.0024 BH for Fy equals 250 newtons per millimeter squared. Okay, so this is an important information to have on the side. All right. So here our A minimum would be 0.0013. I hope I've not written too many zeros. Times the B is 300, the H is 660. All right. So here for this one, our A min is 0.0013 times 300 times 660 for H. So this will give us a 257.4 millimeter squared. All right. So our AS prime is more than the A minimum, so we are good, right? We don't need to do anything with it. Now let's find. So this is for compression reinforcement. Let's take notes. Okay. So that's for these two guys here. All right. So now let's do for the tension reinforcement. Okay. So now let's find the AS. So here AS will be equal to, so the equation will change because there was a compression reinforcement. So AS will be 0. Let me just be a little bit lazy and copy the information from here. Okay. So this is the equation plus AS prime. Okay. So the tension still required is a combination of the compressive and then some equation. All right. So here we get 0.156 times 30 times 300 times 580 squared over 0.87 Fy. Okay. Here, because, so again, these are extra information, which I mentioned them earlier, but since we are using them, it's good that we always show where they're coming from. Most likely because our K is more than 0.156, you would realize that your Z would be, mostly you have to use Z of 0.775D, right? Because you get a Z value, which is less than 0.775D, and then you use that value. All right, okay. So just take a note of that. So here it becomes times 0.775 times a D of 580 plus our AS that we got for 352. Okay. So this then will be equal to 2977 millimeter squared. So again, from here, you can, if you are still using, so let's say for the AS prime, let's say that if our bar diameter is 20, then it means that we'll need how many of this? For 20, the area is 300 for one. So we'll need, so we can say provide 2T20, where the ASP is 600 millimeter squared. Okay, so the area for one is 300 millimeters. So that's it. Then for the tension, we can say that, okay, so let's go with a 25. So let's 5 be 25. So we'll end up providing, okay, so the area of one is what? 500, right? So 2977 divided by 500 will give us 5.9. So let's say 6. So provide 6025. And then the area will be 300 millimeter squared. So far, all that we've been doing is to design this beam. Oops, my screen goes haywire. It's to design this beam. So it seems like it's a lot because, yes, it is a lot. So far, we've done, oh, okay, don't go down, just stay here. So far, we've done the span here. We've done the span over here. These two supports are the same. So once we are done with one, it's the same. So now we are left with the mid span of the second span. Okay, and that'll be the last one. So this is the third one. So it states, let's say the mid span of the second span. Okay, So that one, our moment M is 0 0.0, 0.07 FL. So 0.07 times the F is what? We got F to be 995. So 995 times an L of 5. So this will give us 348 kilonewton meter. Again, let's come and find K. So K is M over BD squared FCU. So it's 348 times 10 exponent 6 divided by so this just like in the first case, this will be designed as a T-beam. Okay. So we got our B to be 1,000, so it becomes 1,000 times 600 squared times 30. All right. And if you do this calculation, you should get if I remember what I had, let me just see if it tallies. Yeah. So this is 0.03. Okay, very small. Okay. Because it's very small, this means that our Z is likely going to be 0.95D. Okay, which is the 570 we had earlier. You can always check and see. So the area, so here only tension steel is required, only tension. Okay, so the AS here will be equal to M over 0.98, 0.87 FYZ. So 348 times 10 exponent 6 over 0.87 times 460 times 570, and this should give us 1525 millimeter squared. Okay, so again, let's use diameter of 25. So it means that we should provide 1525 divided by 500 for the area of 1. So provide 3 and 4, sorry. So provide 4T25, and then the area of that would be 2000 millimeters squared. Okay. So all of that, all that we've done so far is to check for moment. What if we need to check for shear? All right. Okay, so all of that is to check for moment. So let's see how the beam will look like if we are to draw all the rebar arrangement in there. All right, so let me just go ahead and draw that. Let me exaggerate the width of the the width of the beam, or the depth of the beam. How many supports did we have? 2 supports. Okay, so let me just draw the supports. Now we see Let me draw this as my support. So this is what we have for our supports. And let's see how the whole thing will look like. Um, okay. So for the spans, we only needed tension reinforcement. So if you look at the first span that we looked at, we needed 40, 25. Okay, so great. So they are both the same regardless of what we do. So in here, I have my rebar in here. Let me just draw them to show what we have. All right. You can, to make things normally on site, this is what we do. Normally on site, um, we try not to cut too many rebar. So if both of them at the base share similar arrangement and size, we actually join them all together. Sweet. Okay. But again, that'll be dependent on the length of the beam. All right. So you have your anchorage this way. Okay. So this beam here, this one here like this is 40, 25. All right. Definitely the length of the beam, which is 15 meters, is more than the length of the rebar on the market. Most rebars are about 12 meters. All right. So it means that at some points you may have to join the rebar. So you may do some bit of lapping somewhere here. All right. So to exaggerate that, sometimes when you take some drawings, you see usually when you're lapping, you lap where its effects is not great. Its effect is not significant on the behavior. So usually for tension at the bottom, you lap closer to the support, right? So you have something like this. Okay. So maybe you could. I can't get a zero. What is a zero? Okay. So you would need maybe something like this. And I'm just my pen is on off again. This time it's the screen. Okay. All right. So you have something like this. Okay. Then this one continues its trajectory. Right. So this is how we do the lapping. Okay. This guy is so badly drawn. Then we have the anchorage. If there were time, we can look at some of these things, how to calculate some of these, but the quotes actually shows how these things can be calculated, so it's fine. All right. So this is how the lapping is done. Perfect. Okay. Then at the top, we realize that for over the supports, especially with the interior support, we were to provide 6, 60, 25. Let's assume that all the 6 cannot go on the same line, which is usually the case. What is going to happen is that you have so let's say for the top reinforcements using green, you have 1, this way. Then you will have another one that way. Okay. So in some cases, what is going to happen is that there's the top one, which is oops, I'm drawing double lines. The top one could literally continue all the way to the ends, and then the middle one, or the lesser, I'll call it lesser anyway, but okay. So you see that this one spans only the critical section of the, so something like that. Okay. So which means that the here is 3 3T 25, maybe you can call it T1, and then this guy here, the second one here is 3T25 T2 or T2. We'll just do T2 like this. It's fine. Okay. There's no need to bring the hyphen. Okay. Which makes sense because at the supports, we were asked to provide 6T25 for the tension, and also provide 2T20 at the compression zone. So normally it means that in this zone over here, this is a compression zone. This is a compression zone for the support area, all right? But we already have 4025 passing through, all right? So since we already have 4025 passing through, and you have to provide 2T20, then it means that the 4T25 is more than adequate for what you access to provide. So this system is good. All right. So the beam here will support again, assuming that the length of the beam. Any questions? We said that. What time is it? 9, 10, 10, 11. Okay, we'll finish very soon. All right. There's a second portion to this question. Maybe I'll add that one later, and then before I submit this to you guys, so that you can add that one when you're watching. Because it looks like I'm even tired myself. I went to just this morning. All right. So assuming that we want to lap, we can lap somewhere here. That's the best place to do any lapping. Okay. So just like what we had previously, we can just and just exaggerate this joint a little bit. Not this color. Okay. And then so this will also come a little bit further. Okay. So we can end up with something this way and this. Okay. All right. This looks like I'm lapping over here, but I'm not. All right. It's just that I ended up drawing double lines. Let me make this correction so that it doesn't look like they are double lines. Sometimes it can be a bit confusing. Okay, now I think I can just join them together. And it's from here. Okay, this looks fine. Okay. All right. So this is for the case of the case of a continuous beam. All right. Okay. So let me see what we have on this side. So we can add the shear. That takes us a bit more time. So for shear design, there are a few things that we need to find. We need to check the maximum shear stress. So check for maximum shear stress. Okay. So maximum shear stress V is equal to the shear force at the face of the support divided by BD. Okay. So Vs, which is the shear force at the face of the support, is simply 0.6 F, which is the shear force at the center of the support, minus W times the support width over 2. So half the support width. So let's say that our support, I don't think I gave you, did I give you anything about the support? So let's go back. Let's see, for example. Okay, so let's assume a value for the support width. Okay, so let's assume support width. So that's the column, the size of the column. All right, it's equal to 300 millimeters. Okay, so the VS, this might look new to you guys because you've not watched the previous video, but it's something that once you watch the previous video, it becomes clear as day. All right, so 0.6 times the F, which is 995, minus W, which is the UDL, and that was 199 kilonewton per meter, times half of, so this is the same as 0.3 meters, right? So 0.3 over 2. All right. So if we do this, your VS, your big V, which is the shear force at the face of the support, would be 567 kilonewtons. All right, so this is shear force at face of support, okay, which is typically the column. All right, so our maximum shear stress V will be equal to 567. Let's convert that into newtons. And our B is 300, so that's the width of the beam. And our D, okay, towards the support, our D will be 580. So use D at support, okay, because we get different values of D as we go along. D at midspan was 600. D at support would be 580 in this case. All right. So use the D closer to the support. So our shear stress here would be 3.26 newtons per millimeter squared. Okay. And this should not be more than the minimum or the lesser of either 5 newtons per millimeter squared or 0.8 square root of FCU. Okay, so this will be what, 0.8 square root of 30, and that'll give us that'll give us 4.38. All right. So 4.38 newtons per millimeter squared. All right. So since this is not more than this value over here, our shear stress is great. The moment your maximum shear stress is more than the allowable, it means that your failure, when it comes to shear failure, will be governed by diagonal compression failure, which we don't want. All right. So the code limits us so that we don't end up with that behavior. Okay. So let's look at, so normally we would end up providing nominal links anyways. Okay, so let me just go ahead and do that. So for nominal links, it's because I have a period view. As I'm jumping a few steps, all right? But nominal link, we need to find ASV over SV, where ASV is the area of the shear links, and the SV is the spacing of the shear links. Okay. So this equation is 0.4b over 0.87 FYV. All right. So this is 0.4 times 300 over 0.87 times 250. That's what we give for the yield strength of the steel member. All right. So this is going to give us 0.55. Okay. There is a table that we had from the previous lecture. There's a table that we can use to I'm looking for that table just to bring it up again. To find the ASV. Okay, so we can use this table. Let me just paste it for us to see. So this table can be found in the previous lectures as well. So just in case you're looking for it, it's right there. Okay, all right. So we have this table showing nicely. All right. So usually you come to this table and choose a value higher than what you calculated for, right? So let's say we are looking at 10 millimeter diameter rings, all right? So it means that we are going to look at this zone where 10 millimeter diameter. So what do? Our value was 0.55. So the best one to choose is 0.57. All right. So it means that we are to provide R10 links at 275 millimeter centers. Okay, so this is the spacing. So what we see over here, no, different color. What we see over here is the SV. So this is the SV, but SV should not be more than 0.7 G, I believe. Yeah, SV should not be more than this value. That information also can find nothing in the preview. I'm hoping that's what I have in mind. Oh, 0.75. Okay. So there's a 5 at the end. Great. All right. So once we have that, we can calculate. So this is for the nominal links. And we need nominal links when your shear stress is between set some ranges. All right. Okay. So before you come back to this video, I would really push that you watch the what's the name? The one that I sent to you a few days ago. So here our ASV over SV will be equal to 0.571. Because this is what we provided. Okay, so even though this is what you calculated, once you choose your spacing and then everything, you have to tell us what's the new ratio of the area of the links to the spacing would be. So in this case, it's 0.571 from the table, straightforward. Okay. Okay. So this is just on the side, all right? So let's go back and then find the actual shear links that we need. Okay. So we found V. This is for the reason why we chose, if you go back to, did I draw? I didn't draw. Okay, it's fine. I'll just draw it over here. I should have drawn something before. Let me bring it down a little. Great. Okay. So whatever information we have over here, I can do something very similar. So for shear design, so for shear, let me just delete this guy since we will not need them. Those are for the moment. For shear, it's slightly different. So let me put the shear 1, 2 there, so we can work with that. Okay. For shear, this is so 0. Oops, green 0.45 F. On the left here is 0.6 F. On the right is 0.55 F. Here is 0.55 F. And then this side is 0.6 F. And then this is 0.45. Okay. So when we're checking the maximum shear stress, we used the 0.6 because that is what will give us the highest shear stress on the entire length of the beam. Okay. So, so let's take note of it. Okay. What makes design interesting is that most decisions are from the point of view of the structural engineer. All right. So before I go on and do the calculation, some structural engineer would decide, okay, you know what? Sorry, there's an F over here. Instead of me finding the shear for each span, I can pick the higher value and work with that, and whatever I get, I apply to all the spans. And yes, this is what you call conservative design. You are over designing. It might cost your client a bit more money, but in most cases also it protects the building a bit more better in case there's any accidental loading or additional loading. You are good to go, and also it saves time when you are doing all these calculations. Okay, but in this example, I'll go through all the steps so that we see how this is done properly. So now let's look at, so we have supports, right? We have the end support and then the interior supports. Okay, so let's look at the end supports. Let me check if I'm still recording. So let's look at the end support. So with the end support, we find the shear force at a distance d. So shear force at a distance D, have a meeting in the next 7 minutes. So maybe I'll pause, continue with the video, and then post whatever I have done afterwards. Okay. So at the end support share for at the distance D would be, so VD will be equal to, so at the end support, our share is 0.45 F. Okay, let's take a note of that. So we have two end supports. So 0.4 F minus W times D plus the support width over 2. So in effect, if you look at this beam, and then this is our supports, all right. Basically, our shear is at midpoint. So our shear is 0.45 over here. So at a distance D from the face of the supports, then we need to find the shear at the center supports and then subtract it from the shear between the center support to D. And that's like this value here is D plus support width over 2. Okay. So here we will have 0.45 times 995 minus W, which is 199. Our D, again, as we move away from the support, our D will change, right? When we're looking at near the support, our D was 580. Some distance away from the support, and our D will now become 0.66. Or in this case, you go with the worst case scenario, which is the higher D value. Is that correct? No, that's not correct. Let's scratch that one out. All right. So 0.6 plus 0.3 over 2. Okay. So then this will give us 299 kilonewtons. Okay. Now with this, we also need to find its corresponding shear stress. So V equal to big VD over BD. Okay. So it becomes 299 times 10 exponent 3 all over 300 for the B and a D of 600. So this will give us 1.66 newtons per millimeter squared. Now we need to find the VC, which is supposed to be the concrete design shear stress. All right, so VC is the concrete design shear stress. Okay, and to find VC, we need 100 AS over BD and D. Okay, so let's say that our 100 AS, where AS is the area of steel in tension at that section. All right. So at that section, I think we'll have about 40, 25. So roughly our AS here would be 2000 millimeters squared. Okay. So it becomes 100 times 2000. So this is the AS at the section. At the section, so this section right here is where we are finding that AS. Please take note. It's at where we are looking at. So at a distance D from the face of the support. So become 1000 over 2000, B of 300, and a D of 600. Okay. So this should be approximately 1.17. I know it's not the right answer. It's close to it though. Okay. So we go to a table, which again, I gave it to you guys the last time, if I still have it. Oops. I should still have that table somewhere. Okay, let me see if I can find the table. It's here. So this is a table for FCU. For FCU, why can't I write on my screen? Okay, and what is happening to the screen? This is for okay, my screen has given up on me. Anyways, it's fine. This for FCU equal to 30 newtons per millimeter square. For different tables, we'll have different values, all right? For different FCUs, we'll have different, they are quite close and all of that, okay? So here, our 100 AS is somewhere between here, somewhere in this space over here, because we got 0.17. Sorry, we got 1.17. So we're actually between this here. So we got 1.17. So it means that we need to take into consideration these two numbers. Our D, so the effective depth D is more than 600. So because it's more than that, we choose the 400. So it's more than 400. So once we have that, so it means that we'll deal with this zone right here. We'll deal with a 1, so we'll deal with 0.67 and 0.78. All right. So we use a interpolation approach to find our answer. Okay. So the interpolation for finding VC, if I to do the interpolation, small letter VC will be equal to 0.67 plus 0.67 minus 0.76 divided by 1 minus 1.5, then times 1 minus 1.17. All right. Am I correct? So I think so. No, okay. Let me just get this one right. So it's 1.17 minus 1. And this should give us the VC. All right. So this is how we do interpolation. Oh, okay. So that's 4 p.m. Just fine. Okay. All right. So where was I? Sorry. All right. So in that case, our VC will be equal to 0.7. Let me see if I have the same. Yeah, so 0.7 newtons per millimeter squared. All right. So here we have to compare VC to V. So we compare VC to V, and then that would inform us as to what to do in terms of calculating for the shear lengths. All right. So again, there's this table which have already been provided. So I'm bringing the table up again so that we see, because for some of us, this will be our first time seeing this table. All right. This table is to help us to decide whether we need shear lengths or not. Okay. So if V is less than 0.5 VC, no shear lengths at all. If V lies between 0.5 VC and VC plus 0.4, then we provide nominal lengths. So I've done some calculations already for nominal lengths. We'll use that one if our V falls in this range. But if our V is more than VC plus 0.4, then we have to design the lengths and then use this ASV over SV equation. Okay. So let's check and see whether we'll fall in that range or not. So our VC is 0.7. So let's say, so VC plus 0.4 will give us what? 1.1. Okay. And what do we get for V? Our V is 1.66. So V is 1.66, which means that V is more than V is more than what? VC plus 0.4. Okay. So because of that, it means that we need to design links. Okay. So we have to use this equation where ASV over SV will be equal to V minus VC over 0.87 FYV. Okay. So we're using this equation right here in this case. All right. So this will be equal to 300, which is the B. V is 1.66 minus a VC of 0.7 divided by 0.87 with an FYV of 250. Okay. So this should give us 1.32. Okay. So 1.32, again, we come back to this table over here. No, not this one. That one here. So 1.32, again, we are using 10 mm bars. So 1.32. So we have 1.7. Okay, 1.7 is the next highest over 1.32. Okay. So it means that we go with 10 mm bars to provide R10 at a space of 100 millimeter centers, okay, where our ASV over SV would be 1.57. Okay. All right. So just give me some 5 minutes, and I'll wrap things up. All right. Now, we need to check the shear resistance Vn. Please watch the previous video, very important. Okay. Otherwise, some of these things will be strange to us. All right. So ASV over SV 0.87, FYV, sorry, plus BVC times D. Please, this is called the shear resistance. Okay. Shear resistance of concrete and nominal links. Okay. I have explained extensively what this is in the previous videos, okay? So here our V and big V, okay, will be equal to the ASV that we had was and this is where it becomes a bit interesting. So this will be the ASV from the nominal links, okay? This is from nominal links. So take a note. Okay. So I have to go all the way back to our nominal links and see what we had. So our nominal links, this was our what was the nominal links that we provided? Yeah, so it was 0.571. Okay, 0.571. So this becomes 0.571 times 0.87 times 250. So that will be in a smaller bracket. Then plus B of 300. And now VC is 0.7. So times 0.7, then times a D of 600. Okay. So this should be approximately 199 kilonewtons. Okay. It might slightly change. All right. And we need this information to determine the extent. We want to determine the extent of the shear links. Okay. So mind you, this is for shear links for the exterior supports. All right, not interior supports. Right. So pretty much what we are doing here. So let me take you guys to this one. We are trying to design the shear links for this zone. All right. So for this zone, we want to know how far we should go with the shear link. Is it all the way to the end or some distance? All right. So we want to find that distance S. And to do that, we find the Vn. So the Vn is like the shear force at the at one end of where your shear links end. Okay. The other end will be Vd. So mean that our S here will be Vd minus Vn. Okay. Over the UDLW. Now, let me check the equation. Just give me a second. Since we have all of that over here. Okay. So I think it's 5 p.m. All right, so it's fine if you want to leave. I'll just go ahead and continue with the video and then post it once I'm done. All right. Okay. Let me look for this. Okay. So the extent of the shear links would rather be VS, which is at the face of the support. All right. But most likely we haven't calculated VS for that particular support. So this is the same as VD minus Vn over W plus the D, which is supposed to be the distance. All right. It's the same thing over here. So here, our VD, what's the value of VD? VD is 299. So 299 minus the Vn of 199 over W of what? And W is also 199. Interesting. So over 199 plus 0.6 for the D. All right. So once we do that, so this is equal to 1.1 meter. So that's how far our shear length should extend from the face of the supports. Okay, so this is an idea that we need. Now let's look at the last bit, which will be the first and then the first and third spans, or the spans from the interior supports. Okay. So D, so let's say first and then third spans all right, so with that one, VD will be equal to, with that one, I think the highest there is 0.6 F. Take note. Okay. So our VD will be 0.6 F. So our VD will be 0.6 F. Minus okay, you know what, let me just put the values in the 0.6 times 995 minus 199 to bracket 0.58, okay, plus 0.15. So here, this one is our D. This is the support width over 2. So just take a note. That's all there is to it. So our VD will then be equal to 452 kilonewtons. We find the shear stress VE, which is VD over BD. And this will give us 452 times 10 exponent 3 over B, where B is 300 times 580. So that'll give us 2.6 newtons per millimeter squared. Okay. So again, for that space, we need to find, so for that interior span, we need to find the corresponding VC. So again, find VC for interior spans. Okay. So again, we need 100 AS over BD. So I think if I remember, going all the way up there for the interior spans, what do we have? We had 3,000. Yeah, 3,000 for the ASP. So it's 100 times 3,000. Okay, over B, where B is 300, and then D of 580. Okay, so this should give us 1.77. Okay. So from table above, our VC would be 0.81. Okay. So here, our AS, so I'm jumping AS over SVU will be 300, which is B, times V, where V is 2.6, minus VC of 0.81. divided by 0.87 times the FYV, which is 250. So this will give us 2.47. So again, so maybe let's say that one, instead of 10 bars, let's use 12. Now we can see the difference. So 12 links. We go back to this table as we have it. No, not this one. Yeah, this table. And then with 12 and 2.47, we'll go with 2.5. So that'll be 90. And 90 spacing is very small. But let's just go with it, okay? So it means that provide R12 links at 90 millimeters centers. Okay. So it means that our ASV over SV will be 2.1. I think it was 2.511. Okay. So 2.511. So again, let's find the spacing for that as well. So let's say the S for that will be VD minus VN over W plus D. So our VD in this case is 452. So 452, our VN will be the same regardless, right? So VN is 199. Our W is also 199 plus 0.58. The D, and that will give us 1.85 meters. So, so here we will see. So the last bit of it before. So if when you look at that supports that we are looking at, all right. So on this face is 0.6 F, right? Then on this face is 0.55 F. Okay. So far all our calculations was to deal with the face with a 0.6 F. So the next one is the same thing we're gonna do. Already this time around, we are dealing with the face toward the 0.55. All right. So let me say maybe the second span. All right. Where our F is 0.55. 0.55 F. Okay. So again, now you find your VD, and the VD would pretty much be something very similar. So 0.55 times 995. Okay. Then minus 199 for the W, 0.58 plus 0.15, and this will give us 402 kilonewtons. All right. So from here, we go through similar processes like what we had before. All right, and then so we find our we find our V, we find our VC. All right, just to ensure, but in this case, I think VC will be very similar to V, right? I mean to the previous VC. Then you find your AS V over SV, and we could end up with, let's say, maybe R10 links at maybe 150 millimeters centers. Okay, so we can do something very simple. All right, something close to what we have here. Now, the major challenge would be how to represent this. All right, so I'm going to copy the information that we had for the rebar, for the beam. And let's see if this makes sense to us or not. So let's see. Let's just get this site done, and then I think that should be okay. This is 150. Okay. So there are a few things that I've done that I have to keep going back and forth. Is fine, and that's what design is all about. A bit of back and forth. All right. Um. So here, our nominal links. We said that our nominal links is supposed to be R10 at 275 millimeters. Then from the main support, the end support, we were to provide R10 at 100 and 1.1 meters. Then for the interior support with the 0.6 F, we were to provide, let's say, R12 at 90 and it spans 1.85 meters. Okay. All right, so let's see how we represent this in a beam, our nicely drawn beam. Let's look at it. So usually it starts at the base of the support. All right. So let me make sure that this red color doesn't affect us too much. Let me take you off a little. Oops. So let's see. Let me just do some bit of house cleaning. Oops. A bit of house cleaning. I think I got it wrong the last time. Let me get it right. Oops. Go again. Okay. A bit of house cleaning should work. Okay. So I think this should be fine. Okay. Oops. Oh, that's too far. Okay, this is great. And then I take this guy out too. Okay, so this is fine. All right. It's not perfect, but it can suffice. So okay. So let me use this color here. So let's start with the left support. So our beam starts at the face of the support. So this is the sorry, our rebar, and it also extends some distance. All right. So it's going to end somewhere here. Okay. So I will make a mental note somewhere here. All right. So this is where it starts. This is where it ends. So this one is R10 at 100. Okay. And the length it spans is 1,100 millimeters or 1.1. Okay. Um, okay, so because I don't have enough space, let me do this. Let me rather do this. Okay. Okay. So let me just I'm just trying to draw a few things so that it's easier for me to work my way around it. So just give me a second. Okay. So let me just this is interesting. Okay. I hope everything looks good. Mhm. All right, so let me just use a different color over here, maybe blue. Okay, great. So within the space is a nominal. So we have the space here. So let me draw one more line. Okay. So from here to here is a nominal, which is the R10 at 275. This is nominal. Okay. Then on this side is where we have the 0.6. So the 0.6, we got R10 at 90. Yeah, R10 and 90. All right. There's so many things that can go into this, but let's leave it as now. So this is R10 and 90. Okay. And this spacing here, or this distance over here, is likely to be the 1850 millimeters. Okay. Then we can have a last bit. Just add that. So on the right side, we would have something very similar. Okay. maybe let's say it ends somewhere here. So there's another one that starts this way. So this one here can be, let's say the R10 at 150. Okay. So this here is for the 0.4 F. This here is for the 0.6 F. And this here is for the 0.55 F. Okay. There's some extra information here. All right. Because these beams, because these rebars here, okay, they don't go all the way. Some of them curtail. It means that within this zone over here, your VC will change because the VC is dependent on the uh, on what percentage of rebar you have at that particular section. Okay. But here I'm assuming that is the same throughout, okay, just for simplicity's sake. Okay. So this is how typically the rebar is arranged for links. Whatever you are seeing on the left side, we'll do the same on the right side. Okay. And if we cut a section, let's say we cut a section close to the support. So let me call this let me call this one. So these are my grid lines. Okay, they are not well drawn. In your case, draw them well. So these are the grid lines. If I take a section, I need a nice color. If I take a section through, it'll be very close to the support on grid line 1. So I'm taking a section here. Let me call that section 1, 1. I'll also take a section that mid span over here. Okay, let's call it section 3, 3. Okay. Then we take another section at the middle portion of the beam. So let's call it section 3, 3. Okay. So no 2, 2 rather, not 3, 3, because that's already a 3, 3. So this is 1, 1, 1, 1, and then here is 3, 3. Okay, just so we draw the cross section of the beam. Oops, too much deletion. Okay, so this is 3, 3. So let's see how this looks like. Okay, so for section 1, 1, all the beams will have the same outline. So let's not, because it is so this is like so if you take section 1, 1, you'll see that at the top over here we have 3 rebars. Then at the bottom here you have 4. Let's assume that all the 4 can go in this space. Okay, so we have 1, 2, 3, 4. Mostly that is highly impossible, but let's assume that for now. Okay, so it means that our shear links okay, and then this will be the outline of our beam. Okay, so this is section 1, 1. So to name it, this will be So here's our 3R or 3T25. Here's our 4T25. And this here is our R10 at 100. Okay. So the width, so this for section 1.1, we'll have something very similar for section 2.2. So let me just make sure that I have all my dimensions written out nicely. All right. So this is 180, and then 180 minus 660 will be what? So this is 480. Okay. So let's copy the same. Let's just do the same thing for the other sections. All right. Let's look at section 2.2. Oops. So section 2.2, let me take the ruler away. So section 2.2. For section 2.2, what do we have? So the section 2.2, it looks similar to the 1.1, except that your rebar, it's going to change. So what should I do? Okay, so 275. Okay, so let me move the 3.3 a little bit. Let me move the 3.3 to the right, so that I get what I want. Why are you moving with me? Let me see. Let me go back. Make sure that nothing is moving. Okay. So let me move the 3.3 towards the support this way, so that my 3.3 can look what I want it to look like. So 3.3 will be something like this. Okay. So 3.3, I have 325. And I also have another 325 here. So I have 6 instead of 2, instead of 3, sorry. I have 6T25. And at that point, the spacing is R12. That's 90. Okay. Oops. At 90. All right. So this one is section 3.3. Not 2.2. Okay. So I think this should explain pretty much what we have been looking at. Okay. In terms of understanding the beam design. Okay. So if you remember your like first year, no, I think it's second year first semester when we were dealing with CNG 261 and you were drawing with AutoCAD the detailing of beams and slabs and all of that. This is what we go through to get these done. All right. Okay. So section 1 and 3.3 are near supports. Section 2.2 is some distance away from the support. All right. So that could be a misspan. Okay. So I think this should fairly explain our concept to us. Go through. If you have any questions, you can always ask, and then I'll be available to help. Thank you, and enjoy the rest of your day.